It's a very personal subject, talking about somebody's imaginary friends. You gotta be careful with that. Okay, we're live. All right, guys, give it up for AJ.
You win the rainbow paper community.
Good morning. I hope anyone is wake up already. So my name is Marinescu. I'm working for Microsoft Corporation. I joined Microsoft 7 years ago when I started as a developer for the heap management, object manager, and the LPC. I'm not sure how familiar you guys are with these components of the kernel and the operating system. I think that's about all. So today's talk is going to be about the chess game, but you're still going to hear something about here, though. So the chess games shows something like that. So you basically explain how the pieces are on the table, and then I'll go ahead and say what is the first move. And ironically, the black hat guys get to play the white. So they had the first move. And then it's what our move in response to that, and so on. Because you have less time now, I'm not going to talk about Vista. I'm just kidding. So first of all, I want to make sure anyone understands what is the scope of this speech here. So this is not a product announcement. It's not a commitment. This is just me speaking as developer in Windows, and I'm trying to cover the trade-offs we have when we have in heap development, the thinking around security, mitigations. There is no final decision, if you want, for whether this is going to be included or not, and so on, and whether this is the final version or not. So it's just a technical talk. I'd like to share with you guys about the current, thinking about the heap management development. So, as a background, I think anyone knows that exploiting flaws in the memory manager is a wide industry problem. And it's seen a lot of sophistication from both attackers and from mitigation techniques. And at Microsoft, when the trustworthy computing initiative started, it was a huge shift in the culture, and it was it was another side added to the security, another dimension to the security. And this talk is about how it gets reflected in one component that is important for security, but it's not the full extent of the trustworthy computing, of course. So a quick, overview of what was Windows Vista heap management about. So first of all, we look to increase the performance and reliability of the heap management. There is a shift in industry in the way people use the heap manager. The applications written these days have a completely different outlook from memory allocation perspective that were like, 15 years ago, 20 years ago. And at the same time, we try to increase the role of the heap management in defense in-depth techniques. And we also look how we can improve the experience and from the third-party components, application writers, to get a more reliable, secure, and performant application. So this is how we see today the constraints, the trade-offs in the heap management. On one side, we have the reliability, performance. On the other side, we have the security and obviously the application compatibility. If I were to put this slide probably, like 5 years ago, you'll see maybe just performance and compatibility. The security here is back then has the meaning that the code has to be correct, and I mean, a security was not negotiable at that point at all. So if someone asks for 8 bytes, you can't give like 4 bytes or anything else. You have to be absolutely 100% correct. And this was not there, was not negotiable. However, on top of this correctness and problem to the algorithm and everything inside the heap manager, It's this side now where the heap tries to be in the front, because the front line of exploit. It tries to do something to mitigate against this exploit. So the exploits basically assume there is some vulnerability in one application running on Vista, and once an attacker finds a way around it, can use some of the heap internal algorithms or some of the weakest paths to take advantage of that and to take control over machine, run malicious code, steal data, so all this fun stuff. But after all, the mitigation added here is essentially trying to to mitigate an innovation privilege kind of attack to a denial of service and try to crash the application instead of letting the people to to steal data or passwords or some other thing. But it's still a security flaw as far as security concerned. So this is not a substitute for application to fix buffer overruns and nothing like that. It's just one extra level added to mitigate one of those things. So for instance, how would look the world if like every single attacker will put on the screen a dialog box and will ask like, would you like to crash the program? Would you like me to take control over that process, over the system and steal your data? So obviously people try to, to take the default button. So, which is something that the attacker can put. So the point is to try to mitigate those things as much as possible. So historically, these are the major milestones in the heap management. It has this look-aside addition in Windows 24 Service Pack 4. The low fragmentation heap, which is a highly scalable heap extension that has been added in Server 2003, and security mitigations, which came in Server 2003 and XP, Windows XP Server Pack 2. And the latest is what I'm going to talk today about this heap management. To understand a little bit about the context, here is like a high-level picture of how the heap interfaces are laid out and how the heap code is in the system. First, you see in the kernel 32 are the Winter2 APIs, which are used by, which are the most common used by applications. So you'll find functions like local alloc, local free, global alloc, global free, and so on, and heap function. These are mostly thin wrapper on top on low-level NTDLL functions. Here, some heap can have like a front-end heap, which is a very fast heap management on top on the actual heap manager. After that, you see the segment management, which is the place where the blocks are managed, are collected inside the segments. Every block larger than 500, about 500K, it's going to a special code path, which is as simple as calling virtual alloc, and there is some small bookkeeping inside the heap management to know to release these blocks when the heap manager when the heap goes away, and obviously the virtual alloc is called for the heap manager. So we can see in the heap management a few heap block layouts, and I'm going to talk only about the heap blocks because this is the most interesting part for the exploit, since these structures are embedded with the user data. And we have like a pretty standard header, 8 bytes on 32-bit platform. And by the way, if I specify a number of bytes, it's usually, I assume it's 32-bit platforms. Then right after this header is the user data, and these blocks are one next to other in a large array of memory called segments, and these segments can have partial uncommitted ranges. A free block has beside the header also a list entry, which is a double linked entry structure. The difference between headers is basically a flag, which tells whether the block is free or busy. And a look-aside block has an identical header as a busy block, except has a link pointer to the next block in look-aside. And virtual block header has a little bit more information, including a double linked list entry. So this is another way to to look at the block header. So interesting in this part is the size and the previous size. The heap manager uses those fields to coalesce the blocks. Like when you free a block, it tries to find the previous block and the next block, and it tries to merge those allocations together in one single block. And there are some other interesting things there, such as the flags, which can control we can trigger partial code path. So back in Windows, I just take an example from Windows 2000. So here is how the header layout looks from the debugger, and probably this is the one just where you are most familiar with. You can see the size, the previous size, and then on the other 4 bytes you see the segment index, unused bytes, flags, and so on. And by the way, here you have this is a free block. You have the forward and backward link here. The look-aside, short description for the look-aside would be these are blocking a single linked list, and they were designed to be highly performant. A heap allocation has a very low number of cycles cost, and there is no lock or anything on this code path. And essentially, it's an array with 128 such look-aside lists, and each look-aside list may have 0 or up to some limit of blocks linked one next to other. There is the only operation allowed to this look-aside are pop and push. So pop is going to correspond to a free operation, and push to an analog operation. The low fragmentation heap is not as well known as the look-aside and the other heap manager. And this has been added to address a segment of performance at high scalability servers. And I can give, for instance, like in domain controllers, you have some applications that have to be highly scalable and use a lot of memory. And the current best fit policy was not appropriate for such patterns. And the idea in low fragmentation heap is to keep all blocks in buckets that manage the same size. So you'll have allocation buckets for blocks like less than 8 bytes, 16 bytes, and so on. The granularity of the allocation also goes up. So you can have like a larger internal fragmentation at larger blocks, and small internal fragmentation on small blocks. And the interesting thing about this low fragmentation heap is it has some dynamics to detect, some algorithms to detect collisions and contention on multi-threaded scenarios. So it can essentially create multiple structures on a per processor basis. It's not real, it's not per processor really, but it tries to detect collision and try to use as less as possible slots to achieve performance. And for every single, let's say, unit, there is management of same size blocks, which are also very fast and non-blocking as well. Yeah, the difference, there is a difference though in the block header from a looker side block and the regular heap. And for a low fragmentation heap, you have, I said Lucas, no, I meant low fragmentation heap. So in low fragmentation heap, you have a pointer. This is the block header. You have a pointer to a special region of memory that it's allocated to some other place, which does the management of these blocks allocated in the same area. And in order to free a block, the heap management fetches the header of this, the head of this list, and then does the operation on that segment. A free LFH block will have a relative link, which is not a real pointer, is an offset inside the same segment that is used to link several free blocks together, similar to looker sites, but with less degree of freedom of providing a different pointer. We learned so far about like 3 roles that the heap manager had in exploit. So one was to achieve arbitrary write. And another one was to obtain a block and a requested address, which can also be turned on in an arbitrary write, but in 2-step operations. And also I hear about situations where the function pointer, like the commit procedure inside the heap manager, is used to execute arbitrary code. The arbitrary write exploit was actually very simple to achieve in older heap versions. Let's take a look at the x86 assembly code, and we'll see what's happening. So at ECX, we have the forward link. Here is the backward link from the double link list. So we fetches these 2 addresses, and now we try to write at the backward pointer the value of the forward pointer. So if we try to translate this list entry structure, we can an exploit can translate this list entry structure with something like value to write and location to write. So we'll achieve like pointer size write. And there are several versions of using this kind of techniques. One of them relies in the virtual blocks, and another one is just trying to fake a free block right after the allocation. So let's say this was the original allocation, have block 1, block 2 here. And then it was a bug in that application and overrun the allocation with, let's say, 16 bytes in this case. The exploit will try to craft a header which will which will look reasonable for the heap management, will not break right away, and will provide also these 2 value. Whereas I want to write this at this location. And after that, everything that needs to be done is to free this block. And the lifetime of this block, it may be controlled by the exploit in some cases as well. And once this is released, the heap manager tries to collect the blocks. It tries to remove, it finds this is a free block. It tries to remove from the free list. And you see the arbitrary write happening. So we're looking at this thing, so we're looking for these exploits, and we come up with some principles that we're considering. So we do our best to validate before we have write operation. It's very good to have less predictable value that an exploit can use. The use of dynamic algorithms seems to be very efficient in deterring such attacks, and same function pointers, trying to get the function pointer as much as possible. So this was that was this was our response basically to this arbitrary write on the double linked list. So is this very simple check added in the heap manager, which is to validate whether when you work back the chain, you reach the same block as you're supposed to remove from the list. And the advantage, I'm not sure if anyone can follow up this. So basically, I go back on the chain and then come back from that block, and I have to reach the same block. And then the same is for the other side. And the advantage of this is there is almost no performance hit, because we have to do this writes at those locations anyway, so we have to fetch this memory, so it should be in cache lines. And it's on the code path where this extra operation is not really relevant for in any reasonable scenario. Another thing then was the 8-byte cookie added in the heap in the block header. And I get a lot of questions, why only 8 and not more than this? And the answer is the performance here. Because once you increase the header size, the locality loss is going to affect the applications, so it's going to affect the cache locality and the performance after all. So besides, we cannot even add 4 bytes if we want, because we have also alignment requirements. So it has to be like 8 bytes in that case. And the third one was the low fragmentation heap header encoding. And this was basically, instead of putting just the pointer in the block header, we have some value there, which allows the heap manager to reach the actual pointer. And the value, it's depending on some random number, the address of the block, and the heap. And well, this is this is just one usage of this function. You can come up with any algorithms to make it difficult. The reason we had the block address there is to avoid the fetching from a different block or from some other bug the actual pointer. So we kind of need to randomize by that as well. And I think overall the list removal was probably the most efficient way. It's also far to deter those those attacks. And the low fragmentation heap had also some seems to be efficient based on some analysis. The problem is it's not very often used. Low fragmentation heap is mostly used in a server, and only for in few cases as today. So even if the algorithm is probably good, but we don't have enough coverage for applications to use it. And the main question is like, okay, we found it's a corruption, but what do we do about that? And probably if I talk with security guys, anyone will say you just have to to break the process, crash it, and go away. The problem is the application compatibility is at stake, and the outlook from the heap. So the heap manager, it's something that it's it's used for like for a huge number of applications. Like every single application running on Windows uses the heap manager. And the exploits are usually targeting a very small fraction of the whole number of applications. So they are like services, they are some internet facing applications. But if you look at the entire picture, it's a very small fraction of them which is really affected by which is really targeted by exploits. Besides that, there is a huge number of third-party applications. Which also, because have a very low profile, they are not known or not really interested for exploit. So terminating the application is not really a good answer for everyone, and the idea would be to create a way for applications to terminate if based on some option that the application provides. And for this was added a global flag, which can be defined per system or just per image, and a process and application can use it to break when this happens. So after this, it was the next move from the exploit, which is what was the next low-hanging fruit in heap management. And two of them I learned from Matt Conover, where look-aside attacks. which is corrupting the next pointer for the leukocyte block. And another one, it's a very smart way of going around the list removal, exploiting, using the fact that the heap manager has an array of list entries, and it can fake a list entry between two real ones. And you can probably find a lot of information about this in other talks. I'm not going into details about this. However, there is no good way around the low fragmentation of heap as far as I know. But if anyone knows anything else, so please let me know so I can fix it. So our approach to security is so there's a big line between the applications and the exploit itself. So exploits rely a lot in the heap segment layout and the block layout and a lot of internal structures. The applications are very not very relevant for applications, and also seems to have this problem that they rely in consistency in response. Some attacks are relying on attempting several operations, thousands of times, tens of thousands of times until it succeeds. And we try to leverage those kind of information in when we build our attack defense in depth in a heap manager. So the security in Windows Vista, you can look at the security, and we can I can define few things that were done there. So first of all, the block metadata is now encoded in some way, and I'll go a little bit in detail about that. There is an integrity check on block header, which allow detecting part of the problems or corruptions early on. There is some pseudo-random heap rebasing, and there is some limits for that because we don't want to really randomize the heap addresses for the entire address space due to performance impact and fragmenting the address space. So there is not too much flexibility to play with this without impacting the overall system. We have the function pointer is also encoded in Vista. And there is a lot of variations of algorithms as response to usage pattern. And I'll go in some details about that as well. Yeah, I'll just go there. Oh, for the function pointer? Well, it's just sort of some random number. And it's not really relevant. I'm going to talk about this. We have a lot of flexibility to change and update this pretty often. So I'll talk about a little bit about block meta encoding. So obviously, it's a very hot exercise part, and it has to be very performant. We try to make hard enough to guess the right value. This is not an encoding in the sense of crypto or anything like that. It's not the goal for that. We just try to make as hard as possible to put the right value there. And deter the attacks. And again, if there is a buffer overrun in some application, this is still a security bug, even if it's the application crashes or have elevation of privilege. So there is no substitute for fixing that bug either. We try to. The idea is to have a very flexible and contained way of dealing with those algorithms. Because we need to have to update this as soon as we learn about new things. And I'll give an example of the algorithm we can use, like random addresses, address of the blocks, random generated keys. And the thing is, it doesn't even matter. So every time we can, I think even I changed it several times on this Vista already, and doesn't. It's not something you can take and say, yeah, this is how it's going to be encoded. So in comparison, you can see how the block header for a heap block looks in Vista and how it used to be in Server 2003. And so this is the address, so ignore this one. This is the actual value. You can see, well, it's more, there's some quite some higher entropy there. And I specifically mentioned that we have this checksum or check value here to check the integrity of the header. And I specifically put this in a list, and I don't tell exactly which one it is because it does have the flexibility to alternate the location of fields and within some limits, but there is this possibility as well. So currently, I can tell this was, for instance, the size of the block. This provides the size of the block. Here are the flags. Here are the previous size, and so on. But it's not really relevant. And here you can see like the operations done here, and it's just few instructions where the memory is already in cache lines, so it shouldn't be. Actually, it's not a big problem. However, this kind of makes it difficult to debug this thing, and in order to help debugging, we have improved the debugger extension to decode this entry and get the information out of that block header. And so in that case, for the block you saw before, you can see the actual value, like for the size. Here is the integrity check, which tells the block is not corrupted, and so on. I think I already talked about this randomization, and it's not a very good answer to extend the entire address space, but there are some some flexibility within so small numbers. And looking at these changes, we can look back now to see how these were mitigating the known attack vectors. And basically, the leukocytes are not longer used in Vista. The array of free list is no longer used. There is a lot of changes to the block management so this is not longer valid. We have a lot of valid detection of the errors because we have this integrity check, and the all internal algorithms usually need to decode this header every time a block it's used. So it's kind of part of the way the heap is working to get the right value out of the header. And it's going to be a lot of dynamic adjustment of algorithms. And this was not actually specifically for security, but has this security implication. And I'll talk a little bit later about automatic tuning. Obviously, we want to have a lot of flexibility in changing the thing and try to decouple the heap internal structure with with tools and things that really care about the block header layout. This is like how our planning goes ahead. We try to be agile in tweaking all these features. And we also want to be agile in changing the algorithms, also for performance, not necessarily for security and trying to mitigate. So you can look at this like kind of a cat and mouse game because once this is out, in some time, some people can find some other way around this, and obviously we want to update and defeat those as well. You can think of this probably some more what the antivirus does. It learned about a new virus, has like a new way of detecting and fixing this. It's just that it's a very low level at the management in the operating system. What is the benefit of this for the third party? Is first allows applications to be more secure by detecting, allowing your developers to detect early problems in heap management. And we have a lot of flexibility now to detect like buffer overruns, double free to the wrong heap, uninitialized variable, and so on. And a lot of these things are actually already out through the debugger package and application verifier. And there are some limitation in usage of one of those tools, which is the page heap, because of the memory footprint and the performance. This way, an application that was built and was tested on Vista should have the advantage that it's more secure by default, in the sense that it can detect all these errors early on. And also has the benefit of detecting probably even old bugs. If you try to launch an old application on Vista, you may get some of the problem you never saw before. So I'm going to talk now about the other side of the the circle, that we have the constraints and the trade-off, the heap management, just the performance. And here the most important thing is automatic tuning. So it's how we detect a particular pattern or particular usage problem in the heap management, and how can we make the heap manager to tune itself and give the best performance out. And remember that the heap manager is used from those very small devices and up to like high-end servers. So it has to scale all the way from all these from these lines. And we had the low fragmentation heap out for I don't know, a few years already, and the usage for that is still very limited. First, I think there's not enough knowledge that this really exists out there. And secondly, is this inconvenience for the old applications to change the code and enable it. But automatic tuning has the purpose to make the Windows heap much faster by default, to achieve a good scalability on multiprocessor machines. And the trend in industry is to have more processor on the client machine even. There is a huge improvement in the segment management, and the external fragmentation was also lowered. So the automatic tuning it's based on detection of some on patterns at runtime, and we look for contention, we look for some usage pattern, and we try to optimize that code path, trigger different code paths, so that you can get this operation in much faster time. So it's kind of some sort of learning process that the heap manager goes through and tries to improve the performance. And the granularity of controlling those policies are per class of the object size. So you can have some code path for I don't know, some blocks of I don't know, 1 page size or whatever, and a completely different code path which goes to different algorithms to smaller blocks. And it's a lot of lazy initialization principles here to make it very easy to create those this heap manager, this heap itself. And as a side effect, this actually may have some security implication by modifying the the algorithm if someone tries to do like a brute force attack. So the block management is essentially changing the segments layout. So the array of segments is no longer available. We have a lot of improvements in the algorithms. We have constant time where in places when last we had linear, almost like unbounded algorithm. They're not very easy to reach in practice. A lot of those things, there are places where you can reach, but it's not very often hit in practice. So just because of this improvement, it's not like you are seeing any single algorithm, any single program running much faster. So it's just a way how you ponder this to the application performance itself. And there's some fragmentation problems, and we have a lower overhead for 64-bit platforms all over the place, not only for LFH. And by the way, this kind of takes away that bit that people can set to tell not to look after that block, because the algorithm is different these days. And the biggest challenge here is the application compatibility. And the compatibility here is not like the heap manager changes free with alloc and expect people to crash. No, it's because some applications rely on particular behavior, such as first in, first out kind of allocation order, and reading or writing the memory after the block is released, or expecting a realloc operation to return the same value, referring to the wrong heap, and so on. And we learned part of this in the with the look-aside addition. And a problem to the application compatibility is really the distributed binaries. And how we deal with this, first we have to fix the app. So buffer overrun or some heap problem anywhere, it is a potential security hole. So anyone should just fix as much as possible. There are some, we have a very good shimming technology where we can actually, allow these applications to run even if we have those changes in Vista. And the results are very promising so far. And there is a lot of improvement in general in culture. It's a lot of improvement in developer culture. I mean, a lot in the tools and the heap detection, heap error detection. There's a lot of tools out there that can help improving the application as you go on. And I'll go through some results here. So I'll show some performance number, fragmentation scenario, and so here is a test scenario from the heap manager, which tries to allocate from for a number of threads from 1 to 8 here. And each allocation, each thread has like its own, pattern of allocating free blocks. And as you can see, in the Windows 2003, this is the default behavior where the LFH is not enabled, by the way. The look-aside doesn't really perform very well on this because you still have cache collision on the look-aside entries. So it doesn't scale very well. In this case, though, you can see like it's almost linear scalability, and this is just a small test. It doesn't mean like every single heap operation it behaves that way. It's just try to to narrow this part of the behavior. And if we go for larger blocks, and you see in the graph below, this is in the area where the look-aside are not used at all. So the performance is even it's much worse because of the the low contention. So you can see the graph here. What I'd like to point out here is that, and there is one case here where the server is 2003. It's around like 10% probably faster than Vista, and this is when the allocation is a single-threaded scenario. It's single-threaded. And the reason for that is really the look-aside, which are no longer used, but they were very fast operation. So now the segment management and the automatic tuning mitigated a lot of fragmentation scenarios in the past, which are also reliability and maybe even a security problem for people that target patterns for attacks. And this is basically the cost of like a long-term allocation of 80 bytes with for a long time. I actually don't have the time here. This was like 1 minute at the end of the graph. So you see the cost for this may actually be about 5K, and actually visual address space cost. In some worst fragmentation scenarios. The committed memory is also pretty poor in fragmentation in those scenarios, and everything at a very high cost in performance. There are just a few applications, luckily, that expose this kind of scenarios, but it's a huge improvement in this as well. And to look for numbers from a different perspective, we have improving the algorithms for constant time. We get like like order of magnitude in performance from Vista. Also, the segment management allows more space to be used by the process. Usually used to be like an exponential increase in segment size because some other limitations there. And you can see the Vista actually tracks much closer the actual memory usage compared to this spike in the memory reserved. There were a few other where you can look at this. And for instance, one suggestion was, for instance, to put allocation at the end of the pages, so that if someone has a buffer overrun, we'll get instantly an access violation. Well, we actually have this heap in for a very long time, and it's called a page heap, and it's for debugging. However, it's not really feasible to use that kind of scenario on a high-end servers, which already use like 3 gigabytes of the memory, because for every single 8 bytes of block you can use like 2 pages at worst. And so this address space extension and performance is like huge performance difference between the page heap, for instance, and the regular heap manager. It's actually a huge major blocker. But it's actually a very good tool for people to use for to test applications. Another idea. Oh, sure, yeah. Another idea was, for instance, some statistics may show up like I just making up a number now. Like 8 bytes is the most common buffer overrun. So let's just pad this allocation with 8 bytes, so will be okay. Well, the thing is, it's also performance impact because of loss of locality. But it also makes the things even worse by creating a new legacy. So from now on, anyone that allocates is expected to see like more than they ask for. So it's not really helping the security, is really making worse on long term. And separating metadata heap, it's actually has some benefit because it takes away the internal algorithms from the data is controlled by the exploit. There are sometimes performance problems with in some patterns where the block is used right after it's allocated because it's a higher number of cache misses. But most importantly is on long term, we can't tell in that case whether there's an attack or something happening on that allocation, that application, because there is nothing we can tell that has been misused or has been like a buffer overrun. So in that case, the block header, if it's put in if it's in a good way and protected way, it has this benefit of kind of like a seal of the memory. So yeah, so in general, besides like helping the system to be to deter some of these elevation of privilege attacks, it's also beneficial for third party as well. And so basically, yeah, summary. So if you have any questions. This is as often the block needs to be referenced. So even including internally algorithms, when I don't know, we coalesce blocks, everything.
So there's nothing that actually checks to make sure that it's being changed once it's used? There's nothing to check that it's not being changed except for when it's actually being requested. So like if a program was like static for a while and didn't do anything, something else would come in and change.
Oh no, there's there's nothing like that there. Right. Sorry, I can't hear you. So I'm not sure exactly what is the context of extensibility you refer. So this is like every single application. There is nothing special that Microsoft software uses to use this heap. Any single application, Microsoft or third party has all this automatically. I'm not really sure exactly what the accessibility question is. Oh, customer extends to like for the heap debugging. Oh, no, there is nothing like that. There is nothing. There is no support for that. Yeah? So I think the question was if this heap manager is available for security testers. Is that right? Mm-hmm. Yeah. So I mean, once you run on Vista, you automatically get this behavior. The thing is, this is not really protection. So I want to make sure you understand this. It's still if someone has a buffer overrun, it's still a security bug, right? So it's just we try to deter elevation of privilege kind of attacks when the hacker can take control of the machine to crash the process instead. But it's not really protection. You understand that, right? It's try to contain the damage that can happen. Right. It's static. Yeah, theoretically is that way, yeah. So the question was if the header is static or every single system sees the same value, the same mechanism, and the answer is yes.
In all of those, in the cap working list, you have like manually throw in a random number, how to generate it, and you have to store that random number for like a comparison for the store.
Well, so you ask about when you have this random generator number, we store this number. I think the question really depends what kind of what is really the build you are looking at. So we have sometimes in static data. We have some of this in the heap header, and there are several values that we play with. Okay. So actually, the question is it a user mode or kernel mode, or is that the question, or?
No, I was just wondering that. I also wanted to know, when you say you generate a random number, how do you generate it?
How I generate it? We call some functions to to generate this based on some timestamp and some interrupting and that kind of stuff. Okay, thank you very much. Oh. Seriously, we can talk offline. Yeah.